Week 8 video assignment presented by me, Jana Crawford. What reaction is this? This reaction is a nucleophilic addition, and it was assigned by my professor. So what changed between the reactant and the product side? A CH3 methyl group was added to the molecule on the product side, along with the double bond on the oxygen breaking on the reactant side and forming a wedged bond. The oxygen also formed a bond with the hydrogen, making it a hydroxyl. So what are the electrophile and nucleophile of this reaction? Electrophile, an electron-deficient molecule that will form covalent bonds by accepting a pair of electrons from an electron-rich molecule. In this equation, the electrophile is the carbonyl carbon on the silicate enone, which I've circled in red. Nucleophile. A nucleophile is a molecule that donates an electron pair to an electrophile to form a new covalent bond. In this example, the nucleophile is a methyl magnesium bromide, which I've circled in blue. So how do we solve this? First, the nucleophile will attack the pair of electrons in the carbon-magnesium bond in methyl magnesium bromide and break the carbon-oxygen double bond. The electron pair from that bond will move to the oxygen atom and form an intermediate magnesium alkoxide instead. Next step follows a workup from the addition where a neutralizing aqueous acid, in this scenario H3O+, will form the final alcohol product. This will create a tertiary alcohol. The negative charge on the oxygen atom will then protonate to form the final tertiary alcohol. Electron flow. The electron flow reflects the polarity and electrostatics of this reaction. Since magnesium is less electronegative than carbon, there is a strong dipole moment created. This causes the electrons to push towards the methyl group carbon and create a strong nucleophile. The carbonyl carbon is a strong electrophile due to the oxygen atom withdrawing electron density through inductive and resonance results. This causes the electron flow to follow the path from the area of higher electron density to an area of lower electron density. The regiochemistry and stereochemistry. The regiochemistry for this reaction is a 1,2 addition. The substrate is an enone and Grignard reagent that favors 1,2 addition since there is a higher reactivity and basicity of the species. The stereochemistry of this reaction is diastereoselective and is a preference driven by steric hindrance. This means that the nucleophile approaches from the less hindered side of the molecule to avoid being repulsed from the substituents on the ring. The product displays this by showing how the CH3, the methyl group, is added on the dashed line and the OH, hydroxyl group, is added on the wedged line. Since this reaction is diastereoselective, it means that it favors specific outcomes, the methyl on the dash and the hydroxyl on the wedge. I believe that there are no rearrangements because of this. To conclude, the reaction is a nucleophilic addition. It does have regiochemistry by favoring a 1,2 addition. It has diastereoselective stereochemistry, and since it is diastereoselective, I do not believe it has any rearrangements. At this endpoint, I added a reaction sheet that I got from my feel the reaction sheets are a nice, fun, and simple way to organize all my reactions and remember all of the rules that attach.